So are people all across the internet hearing my voice right now? They're going to live stream this. I'm very nervous. Okay. Ready then? Yeah, oh yeah, where do I plug that in?
No, you don't. You just need to put it on the table, I think. That's at least what Niklas said. Okay, that should be working.
Okay.
No.
Cool. Okay, is that close enough or does it need to be closer?
I don't know.
All right, we'll stick it here and see how it goes.
Okay, cool.
Okay, look at all these new Haskellers. This is great. So happy to see you all. All right. So I hope you all in the back have pretty good hearing because I've been really sick with bronchitis, and so I've been coughing and hacking a lot, and so I will try to speak up, but that might be hard for me. So we'll do our best. Tell me if you can't hear me though, okay? I guess you wouldn't have heard me say that either. So, all right. So my name is Julie Moranicki. I'm one of the authors of a book called Haskell Programming from First Principles, otherwise known as Haskell Book. So I have only, Haskell is my first language that I ever learned. And I was never a programmer before. And then when I was 40, someone talked me into learning Haskell. And I didn't think that any of the books that existed for Haskell were very good for beginners. A lot of them relied on you to know some other programming language already. Real World Haskell talks a lot about C, which I didn't know. And they all tell you about, they compare recursion to loops, and I had no idea what loops were and all this other stuff, so I wrote a book. So, so I've only been programming for a little over 3 years, really. And so if you ask me questions about how something in Haskell compares to something in a language that you might know, I might not know the answer, but there are people here who are helping me today who might. So how many of you are already programmers? That's what I figured. Yeah, not very many people learn Haskell as their first language. How many of you, like, this is really going to be your first time writing Haskell? Nice. Awesome. All right. I knew there would be at least a few people here today that were in that situation, so we are really starting from the basics today. But I'm going to try today and tomorrow to teach you Haskell in a really similar way that I learned it. So any of you who are familiar with my book, and not all of you are, and that's okay. It's very, very long. And I knew that some people were going to be here who've never really written Haskell. And some people would be here who really have written a little bit of Haskell. They know some things, but they really want to find out more about monads. So we're going to try to go from 0 to monad in 6 hours. So I had to condense it a lot. So we're going to hit what I think are the best parts of Haskell and try to condense all of that into 6 hours. So we'll do the best we can. Okay. So the way that I learned Haskell, really, or a lot of the way that I learned Haskell was I like to take a very simple thing and then just keep adding to it and refactoring it until, so as I learn new things, then I just keep adding to it, making it do more things, and then refactoring it, like as I moved from knowing case expressions, we'll get to those, to finding out about monad, so I could rewrite those case expressions with a bind, then I just refactor it. So I have several programs like that I started a little tiny one function, and then I've just kept making them grow over time. And so that's kind of what we're going to be doing here. All right, so one of the things I like about Haskell is that the basic idea of Haskell is very small and simple. Right? It's based on a lambda calculus, and we're not going to learn the lambda calculus here, although I would encourage you to do so because it's pretty great. And so we basically have functions, and we have function application, and we have function composition. And our type constructors are also functions. They're functions that create types. And our data constructors are functions that create values. And even really difficult sounding things like monads and profunctors, at their core, they're all just function application and function composition. And so if you start by really understanding what function composition means, everything in Haskell is just going to get so much easier. So that's what we'll be working on today. Yeah, I had made this because I was going to make slides, and well, my build script to build the slides from the markdown file, which relies on pandoc and also a LaTeX package, failed because I didn't have the right LaTeX package to match the pandoc options, and so I don't have slides. I might have slides tomorrow, but I don't have slides today. So we're going to just be live coding all the way. All right. So the way this will work is we're going to start, like I said, from a very simple thing. We're going to start with this little palindrome checker. This is what I started with. All right. Does everybody know what a palindrome is?
Auto.
Huh? Auto. Yes, auto. Yes. So it's a word that's spelled the same forwards and backwards, right? Or you could have number palindromes that are the same number forwards and backwards, right? So this is what I started with, and this is what we're going to start with today. So there will be times when to learn about some of the things, we will write some stuff together, and then I'm going to have you write similar things, but by yourself. So that'll be kind of the flow here. And like I said, there are some people here who can help answer questions if you get stuck on things. But all right, so we have here a function that called isPalindrome that has one argument, right? It takes one word, or one string, and that we have symbolized with this. I forgot I can highlight here. And that we've symbolized with this variable x's. It might be better to use something like word, right, or string as our variable name, but this pattern here of using x's to represent something that will be plural, like a list or a string, so one value that will have a bunch of values in it, is really idiomatic in Haskell. So you will see x's and y's all over the place in Haskell code. Haskell people love single letter variables. I like them less, but it's true that this is how I started off learning Haskell. Okay, so we have a function called isPalindrome that will be applied to one argument, right? That has one parameter, this x's. And what's on the left-hand side of the equal sign is our function declaration, right? It's the name of the function, any parameters it takes. And then on the right-hand side of the equal sign, so all this is the expression that the function name refers to. Okay, so our isPalindrome function is this expression. If x's are equal to the reverse of x's, then we'll return true. And if they're not, then we would return false, and it's not a palindrome. Okay, so reverse. So reverse here is a built-in function, and we'll talk about it in just a minute. It's in the base library, and it'll be in your prelude when you open GHCI. And so is this one. Okay, so the double equal sign is how we check for equality between two things. And reverse is a list. Okay, so this function here is how we check for a palindrome. Let's look at it. I'm going to have to sit down because I'm going to have to type. All right, so let's look at that. Let us go to, oops, I need to go to, whoa. Okay, we need to go to GHCI. So, does everybody have GHCI? Did the person who asked me about when GHCI, did you come? Are you here? Oh, that's too bad. I was really hoping to see when GHCI. All right. So, if everybody will open GHCI. And your prompt, sorry, I probably should have changed my GHCI. Your prompt when you open GHCI probably looks like this. Yes. All right, so the prelude that it loaded, the prelude is a subset of the base library of Haskell. And so you've got, when it loads GHCI, then and it loads prelude, it loads a bunch of functions like the double equal sign, reverse, both of which we'll talk about shortly. Okay, so the prelude refers to that subset of the base library that it sort of automatically loads when you open GHCI. I guess I should have asked, does everybody have experience working in a REPL? No? Okay. A little, maybe a little? Okay. All right. So this GHCI is the interactive version of GHC, right? It's the read, eval, print loop. I think that's what it stands for GHC. So we can type some things in here and load them into here and evaluate them and work with them, type check them. We can also work with, like, get information about, in GHCI, we can also get information about all kinds of things, all things that we've written and things that are in the base package. We can query the types of different functions and so forth, and that's what we're about to do. Okay. So, however, like, I think after you've been writing Haskell for a while, everybody seems to change their prelude prompt to the little lambda. And so, if you want to know how to do that later, we can go over how to set up your GHCI configuration to do that. if it'll make you feel like a real Haskeller. All right, so let us first talk about, I'm still on the wrong thing. Here we go. Let's talk about the double equal sign. So to find out the type of something in GHCI, all GHCI commands start with a colon. Okay, so we will type :type, and that will give us type information about any function. So let's start with that. Now, the double equal sign is an infix operator. So to get type information about it, we have to wrap it in parentheses. Anytime you use an infix operator not in an infix position, you have to put parentheses around it. Okay, so let's get the type of our double equal sign. All right. Did this come up like this for everybody? Mm-hmm. Okay. Yes.
Can I ask you to increase the font size?
In the terminal?
Both.
Both? Okay. Maybe. Yeah. There we go. More? That's good? Okay. Can we do that in here too? No, I don't think so. I don't know what's... Larger. Where was that? There we go. Larger. Did it? All right. Let's do one more. There we go. How's that? Okay. Okay. So the first thing that we have our named function here, and we'll get to the type of that in just a minute. But the first thing that what happened to my, we lost something in our function. This disappeared. Okay. So the first thing, let's talk about that double equal sign. So the double equal sign, everything in Haskell has a type. We have nothing in Haskell that doesn't have a type. Okay? So the double equal sign has a type, and this is its type. I'm gonna have to sit down again to highlight. Okay. So what this type is telling us, these double colons here mean has the type. So that's where we use an equal sign to introduce function declarations. We use this double colon to introduce type declarations. Okay, so the way we read this type signature is we're going to ignore the stuff on to the left of the fat arrow for just a moment, the eq a. The way we read this is this takes two arguments symbolized by a that have to be the same type. How do we know they have to be the same type? They have the same name, exactly, right? If they're both called A, then they have to be the same type. And they return a bool. So the A's in this type signature are type variables, and bool is not a type variable, right? Bool is an actual type, an actual data type. All right, so the A's here are what type? Yes? Right. Right. So they can be any type that has an instance of this type class. That's not going to work. I just have to sit down. The sitting up and standing up, standing up, sitting down. All right. So these A's can be not quite any type in the universe. They have to be types that have an instance of this type class. That's what this information here, that's what it's telling us. So the A's in our type signature have to be something that have an instance of the eq type class. This is a lot of information to take in at once, especially if you've never seen Haskell before. I know, stick with me. Okay? So most types in Haskell do have an instance of the eq type class, but not everything. Yes? What's a what? An instance? Oh, we're getting to that. We're going to talk, because now that we have run into the ugly monster of type class constraints, we have to talk about what a type class is and what an instance is, right? Okay. I'm assuming for now we can sort of keep kind of cargo culting the idea of what a type is, right? I feel like most of you at least have some idea of what that is. So we will get to some special things about Haskell types eventually. But type classes are a little bit weird. I mean, they're not weird, but they're weird in the sense that not everybody has experience with them. So in Haskell, we overload operators with things called type classes. So the eq type class, we can also use our handy dandy GHCI to look for information about that. So this is the name of a type class, and we're going to get information about it. Oh, that's too much information, GHCI. Too much. All right. So the eq class is how, in Haskell, we have overloaded the equality operator. So this is what a class definition looks like. This is what the type class eq looks like. We have two basic operators, equals and not equals. And we see here that there's the type signature that we were just looking at, right? That and that are the same, right? Because that's where this operator comes from. So we can only use the double equal sign with types that have an instance of this. So what is an instance? An instance is how we define the implementation of this function for a given type. So there's a type, maybe I can draw. Get rid of our hello world thing here. All right, so we've got over here a type, okay? So we could have, say, we'll go with some types that we're familiar with. We have bool, we have char, right? We have int. So over here we have some types, right? Over here we'd have a type class, such as eq, that's our one for equality, or ord, that's our one for ordering. So that's where greater than and less than and all those come from. Or that's where they live in their most polymorphic state. We have num. Num is just a disaster of a type class, but that's where addition and multiplication and a bunch of other things are in the num type class. And so on, right? Okay, we have a bunch of other, we actually have show, which lets us, that's the type class that gives us a way to turn things into printable strings so that we can show them like in the REPL. All right, and between the thing that joins these two things is called the instance. Now the instance is a little piece of code that starts with the word instance. So instance is a keyword in Haskell. And it tells you, right, all of the type signatures in type classes, all of these are as general as possible. Okay, so like we saw with the eq signature, right? A to bool. So we want to be able to use this equality operator, the same operator, but for as many types as we possibly can. And the instance over here is where we make it specific to one type. So types and their type classes are linked by these things called instances. And this is how the compiler looks up when you use the double equal sign, for example, in an expression. The compiler looks up, do I know how to implement equality for this particular type? And so it looks for an instance of equality for that particular type. Okay, so types and type classes are linked through instances. Yes. You could. I mean, you can force something like that to happen, but you shouldn't. So, right, we don't have num instances for things that shouldn't have num instances, right? That shouldn't be added, like bools and strings. But you can do, I mean, in Haskell, if you do enough manipulation of your types, you can get it to do just about anything that you want. So I know people who've written num instances for string, for example. So probably there are people who've written num instances for bool. You would just have to, I think you could just, coerce bool into some numbers, right, and add them and multiply them, and sure. So, but we don't have those in base, and I don't recommend you do that. Obviously, you will lose your type safety very quickly if you do things like that. Right? Yes?
it will create a new instance of 5, roll it or true, prime true. Will it be an instance that true?
No.
And that class. Because I can write there true equals true, right?
You can.
Absolutely operator and equal operator. How GCI or how Haskell model what is 5?
So, well, that's a good question. Let's look at what it tells us about what is 5. Let's hide that. Right. Let's look at what it tells us about 5. It tells us that, can you guys see at the bottom? Okay. So it tells us that 5, right, it has a type. It doesn't know what type yet. It's some kind of number. It's something that has an instance of num.
That's a type class, right?
Num is a type class, like eq. Yep. And so because 5 could be, it doesn't want to assume that 5 is an integer, because maybe you just left the decimal off, but really this is going to be used in some floating arithmetic, right? Some floating point arithmetic. And so like really maybe 5 is going to become a float of some kind. And so it doesn't want to assume that. All it knows right now is its numeric literals. All it knows right now is that it's going to be some kind of thing that has some kind of type that has an instance of num. So you can do addition and multiplication with it. But for all it knows, you can't do some other numeric operations with it, like subtraction, because some types of numbers, subtraction is weird, right?
But does this mean that the type class is just enough to perform addition and operation? You don't really have to care about it being
You don't. Sometimes there are reasons to, but you don't have to care about it because it will eventually, during compilation, it will have to default to some concrete type, but it will default to, I think if it's just something like this, where all it can infer is just that it has num, it'll default, I think, integer, maybe int. But if it's clearly something that you're doing with floating point arithmetic, it'll default to like a double. Anyway, I don't want to talk about numbers. So I don't like doing arithmetic. I was a linguist before I was a programmer, and which is why all my programs are about palindromes and things like that. Also, the number situation in Haskell, it's not the best part of Haskell, and we're here to get the best part of Haskell. So going back to eq then. So we have a type class, eq. All right, so we have a type class called eq that gives us this function, double equal a to a to bool. So for a lot of kinds of A's, we'll be able to implement this function. Not every kind. When I first started learning Haskell, one of the things I wanted to know was why eq is even a type class. Doesn't everything have some sensible notion of equality? No. Do you know what the biggest problem is with Haskell and equality?
No.
Functions. Functions are a data type in Haskell, and they do not have a sensible notion of equality at all. So, so that's why eq is a type class. All right. So then over here, we know we've got this palindrome function, and we haven't written or read a type signature for this function yet, right? But we know we're working with palindromes, so it's probably going to be some kind of word. So we'll call this a string, right? All right, so let's say we're going to be comparing equals for strings. Am I writing big enough for everybody in the back? Okay. All right. So then what we need here then, the instance for string, sorry, the eq instance for string will tell us string equals string, right? And that's how we know what we're doing when we compare strings for equality. Okay? So on the one side, we know that we've got this polymorphic function here, right, that can take a lot of different kinds of types. And over here, we know that we're going to be using this with strings. So it's this instance that tells us what equality looks like for strings, or tells the compiler, really, how to implement equality for strings. Now, we don't have to write this for strings. When we write some of our own data types later, we will talk about, if we get there, we'll talk about how to write your own eq instance for your own data types. Right? It's usually fairly straightforward for equality, because usually you know when things should be equal, right? I think so, unless you're writing something really, really strange. Okay, so now let's look at the type of reverse. I told you that that was also a prelude function. And so, reverse. Okay, so we've got this type here for reverse. It takes these square brackets in Haskell are special syntax that mean a list. So reverse takes a list of A and returns a list of A. That is not the most informative type signature it could possibly be, right? Because a lot of things take a list of A and return a list of A. So it doesn't tell us a whole lot. One thing we can get out of this, right, is the fact that in the process of taking this list of A and returning this list of A, it doesn't do anything to the A's themselves. It doesn't transform the A's in any way. The values of the A's, right? There's no function in here that could manipulate the A's when they're inside, right? So we know then that this function is really only working on the list part of it. How do we know that? That's a really good question.
If we take A as an input and return A to 1, solution type, final type will be to a list of A.
It will still be a list of A, but you'd have to have some function working on it in there, right?
Yeah.
But we don't.
Because
Hmm?
The reason why this can't work, because then it would have to be a type plus 1, that you can take plus 1.
Yes.
So, because there's no type plus involved, nothing can happen.
Right. Yeah. Yeah, if you had a type class constraint on the A's, then there would be things that possibly you were doing to the A's in between time.
How we need the type class. If we want to do something, we need to have the type class.
Yes. In order to do almost anything in Haskell, yeah, you need a type class. Almost anything. Yeah. So, yes.
But,
yes.
Playing devil's advocate,
okay,
would still be able to append to the strings, like an exclamation mark, then reverse the whole thing. The type signature wouldn't change. Would reverse, right?
Or remove an element.
Or skip an element.
Well, you can change the length of the list, sure, and still be A to A, but that's, like I said, that's an operation on the list, right? Changing the number of values or reordering them, or those are operations on the list, not on the values themselves.
Will the end of an exclamation mark any type class character?
Yes.
Right, and it's not an A anymore.
Yes. Yeah, then it's a constrained A.
Mm-hmm.
Yes. Okay, so reverse, we can guess from the name. However, what it's going to do to our list is reverse the order of elements. Okay? All right. So our is palindrome function then, we have one argument, right, that we've been calling a string. We're going to look at that more in just a minute. It's going to take the string and the reverse of the string and compare them for equality, because that's what a palindrome is, right? If the string and the reverse of the string are the same, then that's a palindrome. So for example, we can take taco cat. Oh, wait, I got to put it in some string syntax. Taco cat, and compare that for equality with taco cat, right? And that'll be true because it is a palindrome. It's hard to tell there. All right, but we can take, for example, now taco cat and compare that with the reverse of taco cat and get true. But if we do it with, say, my name, which is not a palindrome, we would get, right, backwards it's that, not a palindrome. Cannot type my own name. That's going to be false, right? All right. So far about understanding this function, do we have questions? Next, we're going to look at the type of this function, in case that's what you were wondering about. Okay, so we're going to load that file into our REPL. Oh, sure, you want a main function. All right, so we're gonna give it a main so that it will stop complaining at us. Don't worry about this for now. Let's go ahead and write it. Interactive. All right, so I tried to load it and it didn't like my file because I didn't have a main action defined. So you're always supposed to have a main action defined because that's the entry point for a Haskell program. That is the actual executable for a Haskell program. Doesn't always complain at you about that, and I don't know why it's complaining at me about it right now, but we've defined main now. We will talk about main in just a minute, okay? All right, so I'm going to reload the file now. So that's : reload. And now we compile. So now we'll call main. Actually, let's not first. Okay, so now we've got our is palindrome, and we need to give it one argument. Okay. And that'll give us false, just like it did right here. All right, so what we did here, Julie equals reverse Julie, and what we did here are basically the same thing, right? In case it wasn't clear, because sometimes this is not clear, just function application is just to do nothing. It's just white space, right? You just type the function name, type the argument, and it applies. All right. So now let us look at the type of that function. All right, we've got the eq constraint again, right? That's what this part before with this part, that's what it's called, the constraint. So it's a type class constraint. Okay, so we see that here, right? And then it's a list of A that has some kind of equality implemented for it. So it can't just be any A. It certainly can't be a list of functions. And it will return a bool for us, right? Okay, now we can, and you should, add type signature. So we're going to do that next. So I said that the double colons are like the equal sign in function declarations, right? And we'll read them as has the type. So is palindrome has the type. We have one argument, and we'll go ahead and call it a string. And we return a bool. So string is a type that has an instance of the equality type class. So now we have not a polymorphic type signature anymore. We have a monomorphic one. And we can reload this. And now we have a function from string to bool. So by specifying the type over here in our file and then reloading it, we've now told GHCI this is what we want the type to be. We don't want it to be polymorphic where we could take any kind of list of A. We want a very specific kind of list of A. We want a very specific kind of list, really.
Why do we want to be specific? Couldn't be generically a good property?
It can be. Being generic can be a good property. Sometimes you want to be specific because you want to constrain what kinds of inputs you can get. We're going to constrain the kinds of inputs we can get even further because we're going to not allow numeric characters in our palindromes. So there are times when you want a more polymorphic signature when you don't want to constrain what people could give you as an input. And there are times when you want a more specific one because you do want to constrain what people could give you as an input. So it depends. It's very rare that you really want, I think, in my experience anyway, it's very rare that you want something that's fully polymorphic and unconstrained. But usually you want a set of constraints on them. String is an extremely string is a very specific set of constraints in some ways and opens the door for all kinds of nonsense in other ways. So it's a reasonable question. Okay, so let's now, the next thing that we're going to do is talk about the string type. All right, so that is another thing that we can get. You remember when we had this generic version before we made it monomorphic, we had this generic version and it told us that it was a list of A, right? It's got to be some kind of list of A. And now we see that our string, we made it monomorphic, but that's really just a type synonym for a list of characters. So strings have all of the properties of lists. They're just a specific kind of list. So can anybody tell me what some of the properties of lists are in Haskell? No, nobody? Nobody wants to talk about the, yes?
Well, the one recursively defined.
They're recursively defined, that's right. So there are linked lists that are recursively defined. Linked lists may not mean something to you if you don't have experience with them. I don't know. I'm not going to talk about what that means for us. It does mean that they're recursively defined. That is something that we're going to talk a lot about because we're about to get into how to write recursive functions over lists.
You can get the head, for instance. There's
Yes.
functions defining it.
Yes. So any function that Haskell has defined for lists, you can use with strings because they are just lists, which gives you then a lot of functions, right? Because there are a lot of functions defined for lists. So, yes? Go ahead.
I tried to see the type of string by just putting all type string and then put an error. So why is this?
Oh, because you can't find out the type of a type. So,
Yeah, because it's already defined. But that's the problem. The string was a list of characters. So
yeah, so you can get the type of a value or you can get the type of a function, but you can't get the type of a type name or type constructor name. So you need info for the types, yeah. So type, like if we went with, you know, you can get the type of a certain string, right? It'll tell you that that's a list of characters. It won't tell you that it's a string. It'll tell you it's a list of characters. And you could get the type of like false, right? That'll tell you that's got the type bool. But you can't get the type of bool itself. It'll give you that error. So you've got to do info for a type. Okay. Was there another question? Okay. All right. So them being recursively defined, lists and strings, them being recursively defined means that they can be, they can also be infinite. This is an extremely exciting property of Haskell's lists, right? They can be infinite. So you have to be careful when you're working with lists. If you're going to be doing something that, you know, will recurse over a list, you want to make sure that it will, you know, terminate. Obviously, recursion already has the property that, you know, like if you're writing a recursive function, you already know that you need to make it terminate somehow. But if you're writing something like a fold over a list, the list itself might not ever terminate. And so you have to think of ways to handle that. Okay, so we will look, actually, let's do that next. Let's look at what the list data type looks like. This is one of the things I love so much about Haskell, is that you can look at what all these data types look like, except for the primitives, like int and char. All right, so here is the definition of list. So the list, those square brackets, that's actually the name of the type. Like I told you, they were the special syntax. That's the name of the type. So if we get the information for the list type, we can see that our list type is a type constructor with one parameter, A. A is unconstrained, so it can be anything, any type. And then we have this. Okay, this is how we define what are called sum types in Haskell, or they're a kind of union type. Are you guys familiar with that phrase? Who is not? Okay, so we have different types of types in Haskell. We have product types, which are more familiar to most people, I think, at least most people who've ever been programmers before. So you can, for example, declare a type, like say you have you're constructing users, right, for your web app. And so you've got a user that is maybe a product of, say, a username and a password, right? So then this is your, you know, here you got a type constructor. Here you've got a data constructor. This will, remember I said data constructors in my whirlwind, this is what Haskell is. So data constructors are functions that construct values, right? So your user, then this data constructor is a function that needs two inputs. It needs a username input and a password input, and from that it will construct a value called a user. Okay, so we have product types. And that's a product in the sense that both of those things, like a tuple, have to be present before you have a value of that type. But then we also have these things that are called sum types. List is one. Let's look at a much more simple one. Okay, so a bool, the bool type is defined exactly like that in base. And you can see that it is false, and then this weird pipe thing in the middle, or true, right? And the pipe thing in the middle, that represents sort of the word or, right? It's a disjunction. Because a Boolean is never false and true at the same time, right? We sincerely hope that that is always true, right? So bool is the name of the type. False and true are its values. It sort of doesn't feel the same as like our user type, right? Where a user type, we said that this is a data constructor, which is a function that takes two arguments, a username and a password, and constructs a user. And it doesn't really feel like that with bool because false doesn't really construct anything. It doesn't take any arguments, right? And it doesn't construct anything. But in sort of a trivial sense, we still call it a data constructor. Okay, but these are the two values of bool. So we have false or we have true. So false and true show up at the term level. That's in our functions or in our evaluations of functions. Bool would show up at the type level in type signatures. Same thing here. This user here, the type name, would show up in a type signature like this, and this one would be at the value level. Okay, so if we look at another sum type, this one we will be using more in just a little bit. A lot of people are familiar with this one, I find, even if they don't know Haskell. A lot of them are familiar. Have any of you seen the maybe type before?
In Scala.
Yep. Okay, so maybe is also defined just like this in the base package. That's all there is to it. We have, it has one type parameter, and it's either nothing, right? In which case the A doesn't show up here, right? So this is a little bit like bool's false, right? Or it's just A, and there's the A. This A is a type argument, so this would have to be a type name, and this would be a value, right? But those are going to be the same A's. So a maybe value is either nothing or just A. Okay? We're going to work with maybes in a little while. Some types are so great because you can pattern match with them. Like you can pattern match on each of these constructors so that you can do different behavior based on each one of these constructors. We're going to look at that soon. We're getting a little bit ahead of ourselves because we're looking at list. So here, let's go back to that list type. So we've got on this side, just like maybe, right? List takes one parameter, and it's an A. It can take infinitely many of those because we're going to recurse, but only one. So that means that we cannot have lists that are heterogeneous, right? We cannot have lists in Haskell that have more than one type of data contained in the single list. All the values have to be the same type. They all have to be the same type. They could be different values of that type, but they all have to be the same type. All right, on this side, we have the empty list, right? That's one of the cases of the list type. So the empty list here sort of corresponds to false, right? Or nothing. And the empty list is right there. Here's our pipe, that means or. And here is our recursion. Okay, so the A there, right? We'll have a value of that type A. And this here, this thing here is an infix operator that we often call cons. That may be familiar to some of you. Okay, so we call that infix operator cons, and cons will append this to this list. So if we've got a list that has at least one element into it, then we can keep consing more elements into that list. And this cons operator, here it's in a type in a data type declaration. We can also use it in functions. to cons things into lists. So for example, you can use it like that. So you can see then where the 1 went, right? When we cons 1, cons 2, you get a list of 1 and 2. So that's all the magic there. It's just that recursively we can keep adding more and more things to our lists. Can you define a list with round brackets instead of squares? Yes.
And then we use real type between brackets, so can you define it for any kind of brackets or?
You could make your own data type, sure. That was exactly like a list, but you can't use parentheses because those are taken for tuples. But if you wanted to use some curly boys, or, well, I think actually those are, because you can, not very many people know this, but you can actually write Haskell like, that looks like JavaScript with curly brackets and semicolons. You can write Haskell like that. It's just very few people do. So, but the like the main Haskeller, Simon Peyton Jones, that's how he writes Haskell. So if you go to the GHC DevOps thing tomorrow or something and you're looking at GHC code, you'll see a lot of curly braces and semicolons because that's how he writes Haskell. So so you could, if you could come up with a sum, you can't have parentheses and you can't have the curly braces. Sure, yes. You could write your own list type that use that instead of the square brackets. You can't, like, because the square brackets are a keyword in Haskell, so you can't redefine what the square brackets mean. But yeah, you could define, or you could define it with words. You could define a list type like this. And in fact, I think in Haskell book, we have you do this. Right? And that would be functionally the same thing as this, except for to construct a list, then you would need to call it list instead of putting brackets around it. Yes?
Just so I get the vocabulary right. So, I mean, the colon at the bottom is obviously a function, but the colon in the data declaration, how
it's a function.
It's a function as well.
Yeah. Yeah. We have a lot of type level functions. Like I said, data constructors themselves are functions. Type constructors are functions. If you go up a level from types, we have the types of types, and there's more functions there. So, yeah. Okay, so let's go back to our palindrome. So we're going to be doing a lot of things then with recursion as we work through this palindrome example. Oh, because I had module main there. That's why it wanted a main. Okay. Okay. We can talk quickly about this main. If we can talk quickly. I don't know. All right. We can talk quickly about this main. So what we've done here, for right now, we are using this. Let's see where to start with main. So main almost always has the type, this type, IO unit. We are not going to worry very much at all about what that means. We are probably not really going to talk about what IO means in our 6 hours of Haskell here today and tomorrow. It's anytime you're going to be doing things that interact with the real world, printing things to a terminal, reading from files, going over a network, any kind of thing like that, then you're in IO, right? So all of these functions, like this function here, this cannot print its own result. There is no way here for it to, take input from the command line or from in the terminal, or be able to print the result to the screen. There's just no way in this function. Now, what we're doing in GHC, if we, let me think of a way to, all right, there we go. If we try to use this function without applying it to an argument, we can see what GHC is doing for us under the hood. Under the hood, GHC is using a function called print to be able to print these things to the screen for us. Right, so GHC is constantly doing I/O. But this function here, this has no way to print its own result to the screen. Whereas main, since the whole goal of main is to interact with the real world in some way, right, to produce some kind of effect, to run your program in a way that will affect, you know, your file system or the network or whatever it is that you're doing, then main pretty much always has to have the type IO something. Usually it's unit, which just indicates that it's not returning a value. It's just doing effects and then stopping. Okay, so that empty parentheses there just means that it doesn't return a value at the end. All right, so then we have our definition of main here. We are not, for right now, going to worry about do. Do is a special kind of syntactic sugar over monads in Haskell, or applicatives actually now. And so we will talk about it tomorrow, what it means, because we'll be getting to monads tomorrow. I'm confident of that. And so for now, we will just understand and appreciate the fact that do lets us write some things in a kind of nice sequential order so that it's, you know, we can kind of understand what's happening with this program, right? This get line here, this does I/O. Let's look at the type of get line. Get line is also in your prelude. It's a base function, or we'll call it a function. That's good enough. So get line has the type IO string. So basically get line, when you call main here, because we have this loaded, right? We loaded that into our REPL earlier. So if we call main, see how now it's just sitting there waiting for me to do something? The cursor is just sitting there waiting. So get line is just sitting there waiting for a string to come in. Now, getline's not very picky about what it calls a string, right? Because a string can be against anything between quotation marks. So it's waiting for something to come in, right? And so if we type my name there, then when I type my name here, that string that I just typed into the terminal will get bound to the variable name word right here. That's what this backwards arrow does, is it binds the result of this to this variable name. Okay, and then down here on the second line, we'll have, you know, here's our function that we wrote, is palindrome, which will get applied to that argument, word, and then we will print the result. Right, so do syntax makes for a nice kind of readable, sequentially ordered, you know, way to write your main action. So we're going to use that for now. Tomorrow we'll talk about the monads underneath. Yes?
Can we use there an assignment, word, assignment deadline? Do we have to use this bound operator?
Yes, we have to use that backwards arrow. Yeah. Okay, so when I hit return, after I've typed my name into the REPL down here, when I hit return on that, it will do what? Is it gonna what's gonna happen? It's gonna yes, that's right. It's gonna print the result of is palindrome this word, Julie, right? And so it will tell us false. Okay. One more thing I want to tell you about quickly. Surely this will be quick. All right. I have a special thing turned on in my GHCI configuration that tells me the type of any expression I evaluate in my REPL. So you don't, when you see this it refers to the last thing you evaluated. You don't otherwise need to worry about it. If you want to turn it on, it's this. But plus T will turn on the type thing so that for as long as you have this session open, it will keep telling you the type of everything that you evaluate in the REPL. I have it turned on all the time in my GHC configuration, and I forget to turn it off before I start teaching people, and then they ask me, what is going on there? My REPL doesn't do that. So, all right.
And that's useful for debugging.
It is, yes. And since a lot of the time, when I'm in the REPL, a lot of the time I am teaching, it often helps as well, like, because then oftentimes, like, there's nothing to talk about here, right? That's not an interesting type at all. It's just the empty type. So, but sometimes after it's evaluated, like being able to see the type and talk about it is really helpful. And so I just leave it turned on all the time, and then I forget to tell people. I have some other stuff turned on in my configuration that you'll get to see later.
Could I say you set -T to stop it?
I really don't know.
Unset. Right.
Is it unset?
Some flags does not
Nope.
working on, yeah.
Yeah, I'm not sure how you unset it.
Okay. Also, unset maybe?
Maybe unset, yes. Let's try that. Yep, now it went away. Okay, I'm gonna turn mine back on though, because I like it. All right. All right, so now we have our first little interactive program. You've written your first program in Haskell. Congratulations, everyone. All right, now, the way I started, as I said, the way I sort of learned Haskell, I learned Haskell kind of as I was writing the book, the big giant Haskell book. I was sort of also learning Haskell at the same time and trying to stay a little bit ahead of where we were in the writing process. So a lot of the way that I did it was to implement for myself a lot of the basic library functions, because I wanted to understand, as I've said a couple of times, the thing I really like about Haskell, like this is why, I mean, I was just never a programmer before, right? I was a linguist. So for me, right, I was a linguist. I want to understand language. And for me, the attraction to Haskell, like I knew a lot of people who were computer programmers, and it was just never attractive to me at all. But the thing I really liked about Haskell is that as a language, you can understand almost all of it. Almost all of it is just very understandable. And so for a linguist, that's very appealing. And so I taught myself Haskell largely through implementing the library functions. So I have implemented for myself, I have implemented reverse, for example. So I know exactly how reverse works. We're not going to implement reverse today, but we are going to do some other functions that we are going to need to expand on our is palindrome example. So the next thing we're going to do, does anybody want to take a quick break? Yes, okay. Let's take like a 5-minute, 10-minute break, something like that, and then reconvene. Yes, okay. Do I need to pause stuff? Okay. Okay. Hi, yes.
Hi, I'm Tiz. I want to say hi to a big fan.
Oh, thank you.
Of your book. I started reading it beginning this year, and it's my first serious attempt to learning Haskell. And it's been great so far.
Oh, good. I'm so glad.
I started with the reader chapter.
Okay.
So I'm like 3/4 in it, and I've, you know, it's so good that I took the effort to try to make it a bit better.
Okay.
So I sent you guys a lot of feedback for each chapter. And I was wondering, did you get that? I was writing it to the Zendesk.
Oh, yes, probably.
Yeah.
So there has been, let me think of how to. So right now, it isn't clear who is going to own the book.
You know. dispute?
Yes.
Oh, I'm sorry to hear that.
Yes, thank you. So, yeah, so, I can't talk about it very much right
Is that
now,
right?
but that's why nobody's answering emails right now.
Okay.
Sorry.
But I just wanted to make sure that those bad and
Okay. Yes.
medical things I was sure I couldn't prove did show up at you.
I bet, but we can real quick. Has it been recent?
I think the last one I sent 2 months ago.
Okay.
Yeah, that should show up in the email.
Okay.
It's Matthias at bullbites.com.
Yes. Yes, they have shown up.
Okay, cool.
Yes. So
I said this was one of the big reasons why I attended this
Yes.
conference, that I want to make sure that it arrived.
Oh, yeah, wow. Yeah, I'm sorry. Yeah, the dispute's been going on since October, and so nobody's been really answering the emails since about October. So yeah, sorry.
I hope you get over that.
Thank you. I think we're maybe almost there.
All right.
So yeah.
But just at the end, with Sam is a okay. I'm thankful.
Thank you.
Yeah.
When is your has your book printed to buy? When is it published? Printed.
So the dispute that I was just talking about will have to be settled first, and yeah, that's
It's one page enough to print. So that's
yes, yeah. But we have talked to a printer and we've ordered proofs, so like we know it can be done. But
Okay.
yes, it's a very big book, and you know what, yeah. But it should be.
Because I need paper.
Oh yeah,
I just don't like
yes,
PDF files.
yeah. I don't blame you. So it should be printed and yes.
I just wanted to introduce myself to you.
It's really nice to meet you. So yeah, I'm gonna recognize you.
Okay.
Yes. Is this your song?
Yes.
Hi, how are you?
Hi, thanks.
You should try to follow along with me instead of following me. So we're gonna do the reversing again in Chinese.
Okay, yeah. Well, soon we'll shift to writing.
No, he tried to because he wanted to come with me. Wanted to be broke.
No, not at all. So I'm hoping it'll soon we'll start writing. That was a lot of information.
Yeah.
They are. They came with me, and they have. In America, people don't like for children to be out by themselves. So when I told the organizers here that I was going to bring my children, they said, "Oh, well, they could go to the zoo by themselves." And my children were just so excited. In Switzerland, we can walk around by ourselves. So they've gone. I think they took the train from here and went back to our Airbnb. And I keep texting them, "Are you guys okay?" Because I'm not hearing anything from them. So, are you guys okay? And they say, "Yes, we're fine." So I guess everything is okay. But they're very excited to just.
It's a very friendly place.
Yes. So, and I'm sure they're fine. And, he has a phone, so he has Google Maps and everything. So I'm sure they're fine. But
Quando vi
you
massa
know,
di
some are
operazione,
oh, here's
scusa
mom.
recursiva,
Io sono sempre
reverse from the rest.
Is your brother here?
He was off at different stairs.
Okay. How are you guys doing?
Okay.
I'm fine with the. Maybe not. Do we have our one?
Ja fotografiere tego. Jetzt können wir den miteinander sprechen.
Er hatte gar keine Zeit. Wir haben Zeit.
Ja.
Yes.
Yeah.
Yes.
Yeah.
That's just the name of the ceremony. That the name of the ceremony.
Oh, I see. This is the ceremony.
Yeah. It's a little bit weird, but my parents' fault, not mine.
Nico? Nico?
If you have questions during the talk and don't want to interrupt Julie, you can just ping your questions on Slack and get our attention and raise your hand, and we can give you individual explanations or something. If you're afraid to ask, I don't know.
It's intimidating.
No. I don't know. If you don't want to interrupt the flow, but in most cases, just ask her. Something is not working, which isn't working good. Okay. Cool. And the Slack channel is #beginners, I think, or #beginner. You'll find it.
Here we go.
It's basically this politics. Two different ways of one used maybe people would be
Ja, wir kämpfen mit dem Handy. Was soll ich denn?
Wir sind nur eine Luxusprogramm.
Ich habe die Frage bekommen. Gestern bin ich wieder am Fahren zurück. Ich wollte da weg sein. Ein anderer Nach einer Stunde ich bin ich dann zurück. Kannst du nicht entscheiden? Ja. Alles so groß. Screen is good. Expensive. So it doesn't work at all. Okay. Oh, maybe that's why it's working.
No, like, I mean, it's uncut.
Okay. Are we ready? Okay. Most people came back, so that's good. That's good. All right. Do we have any questions about what we've done so far? That was all perfectly clear?
Yeah.
Wow. Okay. You guys are much faster learners than I was then. All right. So the next thing we want to do, okay, because as I said, this is my first working Haskell program, but then I was very dissatisfied with this situation here. Oops. I'm in the wrong window again. Okay. I was very dissatisfied with this situation. We know Taco Cat's a palindrome, but what if we put a space in it? Oh, it's going to tell us false. Why does it tell us false? Because of that white space, right? Computers are really dumb, and they don't know that white space should be ignored, right? All right, so we are going to do a fairly naive way to get around that. There are better ways to do this in Haskell, but this was how I did it first, and we will learn something good from doing it this way. So we want to have a function. We'll call this ignore spaces. That's not exactly what it does, but it will have the effect of ignoring spaces for us. Okay, so let's look at, we're going to talk about a couple of functions because I don't think I'm going to make you write words by yourself. So words is a function in base. I'm going to silence my phone now that my children have come back. Excuse me for just a second. Okay, so words is a function in base that you can implement yourself. Everything in Haskell almost can be implemented yourself, and it's wonderful to do that, but we're not going to do that. So words, you see that it has the type string to list of string, and that means that when you give it a string, let's give it a string that has some spaces in it. What it will do is break this string that has spaces in it into a list of strings that don't have spaces. So it breaks on the words, right? And it will give us back this list of strings that no longer have spaces. Well, now we have a list of lists. And so I don't know if you're familiar with, I should still spell these out. You can, as I did here, without telling you what I was doing, you can abbreviate these GHCI commands. So they always start with a colon, and so you can type out type, or you can just do :T, and it will mean the same thing. So we have another function that we're going to talk about. Let's go ahead and look at the real type signature of concat first, and then we'll talk about why it's like this. Because this, many people find this to be a very difficult to read type signature, but we can also look at the type of it specialized, I think, for this. Okay, so this syntax here, this is enabled by an extension called type applications that you probably don't have turned on in your GHCI, but it's a very useful tool for teaching. So I will tell you how to turn that on shortly. Let's look at the type signature for right now. This constraint here, foldable T, means that this T is something that is foldable, right? I said we're going to talk about folding functions later. So you can think of this for now as being something, a list or something list-like. So when we specialize this function, concat, right, to actual lists, we can see that now it has the type list of A to list of A. So it's going to take a nested list and sort of unnest it for us, right? It's going to smash it into one list. All right, so if we take now, right, with words, we had we did this, and we made a list of lists. And if we now take this list of lists, and we'll copy that, and give that to concat, it will give us back a string with no more spaces. Right? The same string, but just with the spaces eliminated. Like I said, this is sort of a naive way to do this in Haskell, but it does work. So for me as a naive Haskell learner, this was how I did it. So that I could give it taco space cat and it could still understand that that's a palindrome. All right, so what we need to do then for our ignore spaces function, right, for this function over here, is we need to combine words and concat on the same string. Right, so it's going to have one parameter again. And can anybody tell me what the type signature of that is going to be?
List of strings.
Yes, string to string or list of A to list of A.
List of A.
Huh?
List of A to string.
Well, concat is, but remember, our ignore spaces is going to combine words first, and words takes a string input, right? Yes. So words, right? So ignore spaces is going to combine in some fashion that I'm not going to tell you, right? Concat and words on the same string input, right? So words is going to go from string to list of string, and concat is going to go, say, from list of string back to string. And so our type of ignore spaces is going to be this string, the input string, to the result string. This business in the middle, where it's a list of strings, we don't have to reflect in the type signature. Okay. So there are a couple of ways that you can combine concat and words in the correct order to operate on a string. Turn it into a list of strings. Concat then turns it into a list of strings and kicks the string out the other end, right? Like a little Rube Goldberg machine. There are a couple of ways that you can do this. Take a moment. Some of you, I can tell you're already done. I know. But some people are not. All right, so we're going to have concat and words somehow operating on that string. Can we just do that? Would that work like that? Yes.
Exclamation.
Yeah.
Yes, parentheses. What were you going to ask?
I would suggest to put $1 after concat.
Put $1 after concat. All right, you're a real Haskellr. We'll talk about the $sign later. Okay, so now will this work if we parenthesize it like this? Yes, right? So we go over here and my. All right, we'll reload that file. Everything is compiled. That's wonderful. That's what we want. So now we'll give it a string that has space in it. And it takes the space out for us. This is great, right? All right, so what is another way we could do this? If we wanted to think of these as one function. There's an infix operator we can put in between them that will sort of fuse them into one function. Does anybody know what it is? It's the dot. Yes, the dot. All right, so we're going to talk about the dot next. How many of you are already familiar with the dot? Okay, great. That means we get to explain the dot. So the dot is function composition. The dot composes two functions into sort of one function. And one of the benefits of doing it this way, as opposed to doing it with the parentheses or the $sign, one of the benefits is that in the compiler, it does actually sort of fuse these into one function. So it's quite efficient. It's also that if we fuse them with function composition, we can take off this argument and write it like that. Right? This is what's called point-free style. The points referring not, as you might think, to the dot, but referring to the argument. So you can have argument-free style if you like. I don't usually write my Haskell like that, but lots of people really love it. I think Haskellers favor anything that is sort of maximally terse, right? Maximally short. And so they love to take off the arguments and have these composed functions like this. So that's fine. But even if we're going to keep the argument, it can still be worthwhile to use function composition instead of nesting things in parentheses, as we did at first, because of the sort of fusion effect that you get. Okay, so let's look at the dot in a little bit more detail. Okay, we're going to look at the type of the dot. The dot is an infix operator, so to get the type of it, we do need to enclose it in parentheses. All right, and here is this great type signature. Yeah, probably in maybe my first week of learning Haskell, someone presented me with this type signature and said, "Wasn't it obvious what it does?" Is that obvious to? I think if you're really familiar with math, right, this maybe is obvious what it does, but I was not. I'm a linguist, for heaven's sake. It's not obvious to me at all. All right, what this does is I'm going to go back to drawing, okay, because we already have some writing here, right? So this dot has the type B to C to A to C to A, oops, sorry, yep, to B to C. There's the A to C. Okay, so these things here, when we read this type signature, this here is a function, right? And this here is a function, right? So this dot then is an operator that takes two functions, function 1 and function 2, and then an a value, right, as its arguments. And it gives us a way then to pass this a argument to this function as its input. So that function returns a b, and this b gets passed to this function, which returns a c, and that c is our result. Now it's perfectly clear, right?
But the arrows are implementation, right?
Huh?
The arrows that you draw through it's not obvious from the type.
Well, it's obvious from the type signature because, well, I think obvious is too strong of a word, but you can tell from the type signature because this A here has to get to a C somehow, right? And so you can tell. Now, what was confusing for me initially is that, well, how is this thing not just an input to the very first function, right? But just the way you can nest them right? We know if we nest them in parentheses, that first words would get applied to this, and then that this would get applied to the result of this, right? We sort of, I mean, I think most people, at least, if that's not obvious to you, then please let me know so I can explain that better. But I think with the parentheses, because we're sort of used to that notation from, say, math or something, right? We have this idea that, yes, well, here's our argument, here's our A, right? Here's our argument. So of course, words will get applied to that first, and then the argument to concat will be the result of this expression in here, right? Function composition is doing the same thing.
It's, to me, at least, it's a little bit weird also in the math class, because you write things from left to right and you apply it to right to left, and it's a little bit. But I think there is another alternative version of composite that allows you to write the function in this same order, left to right, in which they are applied.
Yes, there is.
I don't remember how it's called, but it's.
It is. I think it's. Is it the and sign or bracket or something like that? Yeah, I don't ever use it. The guy I work with, Chris, he uses it all the time, and it's. I think it might be the ampersand, and it's like flip, compose. Yeah. And so it lets you do them in a more natural order. I don't know why Haskell has a few things like that where things go backwards all of a sudden. Right, bind is like that too. When we get to monads, we'll talk about bind, and the arguments are in this backwards order. And
why do you work
that's an excellent question. You need them around because you need them to. So with infix operators, there are a lot of issues with fixity and precedence and associativity. So precedence means what order things will happen, right? So like trying to think of something that has, so function application has a higher precedence than, this is a bad explanation. I started down the wrong road there. So it has to do with the order in which things will happen. You want those two functions to fuse into one function first, because otherwise, if you take the brackets off, like this, function application right here will take precedence over fusing these into one function. Because you want, okay, so this thing here has to have three arguments. It has to have a B to C function and an A to B function and then an A. But because of the precedence of this, because of the fixity of this operator, I'm trying to come up with another word because I think, are you all familiar with the word precedence? Okay, so because of the precedence of that operator, when it's sort of reading this whole thing taken together, function application has a higher precedence. And so this would happen before this. And so it would look like you have the wrong number of arguments. Yeah, it will read it like this. If you don't put the parentheses around concat and words, it will read it like this. And so it will look then like this doesn't have all of the arguments that it needs. So somebody brought up the $sign a minute ago, and how most, well, assuming Haskellers were even going to have the argument there, how most of them would write it is with a $sign there. This $sign is this $sign is just a symbol for function application that has an extremely low precedence. It has the lowest precedence it can possibly have. And so if you use the $sign, it has the same effect as putting parentheses around concat and words. meaning that function application, the application of concat composed with words to your argument, will happen after concat and words is composed. Without either the $ or parentheses, then words excess would happen first. This would happen first. Left to right. And so, yeah. And so the parentheses give it a signal that like this stuff in here needs to happen first, right? Or the $ will do the same thing. When it hits the $, then that function application will be the last thing to happen. And so then you have the right number of arguments for your dot. So you can, when I'm not teaching, I am also guilty of using the $ a lot. When I am teaching, I try to use parentheses because those are more familiar to everybody, but this is the same thing.
Can I use the dot as a prefix operator?
You can. By putting it in parentheses.
But I still need to do the parentheses then, around concat words and the access.
Well, let's find out. There's only one way to find out, and it's not asking me. You got to ask GHCI. You got to ask your type checker. Fine.
Yeah, but then what's the precedence now? The word access has a precedence, so.
Oh, well, because now that you've moved the composition operator to the front, the precedence doesn't matter anymore. Because precedence is only really an issue for infix operators. Okay. Yeah. So, yes. One of my best friends is a Lisper, and so he really hates infix operators. So whenever he writes Haskell, he moves everything to the front because then you don't have any issues with precedence anymore. Yeah. So yeah, that will work as well. Oh, I forgot that I'm being recorded on the internet, so he probably just heard me say that. All right. Okay, great. So we have understood function composition now, yes? Okay. So with our what did I do with my pen? Okay, so we had our dot, and yes, you can use it prefix, and that will eliminate your precedence worries. So that was B to C, to A, to B, to A, to C, and we are using it with concat and words. So concat here is our B to C function. Words is our A to B. We know our A is going to be the string input, right? And so words then will give us a string to a list of string. And concat will give us a list of string back to a string. And so the type then of concat composed with words is string to string. Right? Something happens in the middle, but we don't have to care about it because our type signature reflects the input and the output. The type signature of our spaces function here, right? String to string. You can have list of A to list of A if you prefer. For now. In a moment, we're going to do something with the actual characters. And so then we're going to know for sure that we have a list of characters and not a list of some other kind of A. Okay? All right. So any questions about composition then? Okay. So I like to make sure people understand it very well because I think understanding function composition is the key to understanding so many more things in Haskell. When I realized that very difficult sounding things like profunctors could be reduced to function composition, for example, it just made my day because function composition is something I understand. Profunctors, I have no idea what that word means. So It's really important to understand how function composition works. It is weird because things go kind of backwards, but it's a fairly simple idea. If you can nest things in parentheses, then you can compose them with the dot. Composing them with the dot does give you some efficiency. It also allows you to partially apply them, and so pass around this sort of partially applied function, which we haven't talked about yet, but we will. All right, so now we want to use this ignore spaces so that taco space cat can be found to be a palindrome, right? So we are going to incorporate that here. We're going to need another parentheses, right? All right, is this going to work? I have to ask our compiler because we don't know. We're dumb humans. Okay, let's try it. Taco cat. True. We have success. All right, questions about where we are so far? Awesome. Okay, then the next thing that I found dissatisfying in my taco cat quest is that if I give it, for example, let's pretend it's a name. He's Mr. Taco Cat, right? So we capitalize 2 of the letters. What's going to happen now? It's going to be false, right? Because, again, the computer doesn't know that lowercase t and uppercase T are the same thing. I mean, the computer's right in some sense, right? They're not the same thing. But for us, intuitively as humans, we think that they are. So now we want to do something about that. I want this program of mine now to recognize that this is still a palindrome. So we need to do something about the uppercase letters. All right. So we're again going to do, I have chosen a particular way for us to handle this. There are other ways. Yes? What I was just about to do. All right, so we're going to now write a function that we'll call ignore caps. All right, so we've been talking about strings and how they're really lists and how they're really lists of characters. So we are going to go looking for functions on characters. Okay, so what we're going to do now is go to, oh dear, hello. Go right here. Okay, so this is a module in the base library that has a whole bunch of functions on characters. So we're actually not going to look for this in Hoogle yet. We'll do that in just a second because Hoogle is cool. All right, so one way that we could find something to help us out here, one way is we could scan through this, right? Here we have the character type, char, and that's not a data type that we can implement ourselves. We're not going to look at that. But we have, let's see, character classification. We have all these functions here. Is control, is space, is lower. So these all return a bool, meaning that they tell us whether something is or is not that thing, right? Is lower will return true if it's a lowercase and false if it's uppercase, right? For example. So we have these functions. We have, let's see, is punctuation. All right, subranges, right? If you only want the ASCII characters or the Unicode characters. Case conversion. So this will give us, if we give it a lowercase, it will give us an uppercase, for example, right? So in this module, we have a bunch of handy character functions. Not all of these are in Prelude, but they are all in base, so in the standard library. And remember I said that Prelude is a subset of the base library. So some of these are in Prelude and some of them are not. And I'll show you how to get the ones that are not in just a moment. All right. So you saw that these ones up here are take a character and return a bool, right? Because they tell you true or false. These ones take a character and return a character because they convert a character, right? So if we were There's Hugel. Somehow got off on my bar. Okay. Another way that you can, rather than going and looking through a module to see if you can find what you're looking for, okay, we have Hugel. Hugel's there's actually another one called Hayu. Those Haskellers are extremely clever in this way. Okay, we have another API searcher called Hayu. Yes. So Hugel is the more commonly used one, and it will let you search through a lot of the libraries that are on Hackage. Certainly, most of the base library you can search through. You can search by operator. So, for example, if you want to know what this is, you can search by operator. You can also search by type, and it's a fairly useful tool. So if you knew that you needed to do a character conversion, right? Because you've got these uppercase letters and you need to convert them. So you need a character-to-character function. You could go looking here. And oh, look, the one that we need is right there. It's the top one. Hugel is extremely good. All right. So those are some ways that you can go looking for these library functions. Okay. As it happens, some of the functions in this package here, in this module here, data.care, some of them are in Prelude, I think, but most of them are not. So you can, okay. So since they are in base, you can import them quite easily right here in your REPL. You can just type like this, and that will import them into this GHCI session. You can also, since we are working with a file, you can type it up here. And that way, every time we reload the file, those functions will all be made available. Since it's part of base, you don't have to add it as a dependency or anything. We don't need any kind of dependency management here. It's just in base. But since it's not in Prelude, we're going to load it. We're going to import it so that we can work with those functions in the REPL. Okay. All right, so our function here, right, this one is going to be similar in some respects to our one that we are ignoring spaces. So it's still going to be a string to string. Now this time you can't, I mean, you can write list of care to list of care if you want to, but this time we know that it's going to be characters because we're going to do some character conversion, meaning we know what type is in the list now, right? So no longer can it be list of A, the list of A. So you can write it like that if you prefer. String is just a type synonym, nothing more. And type synonyms are kind of bad. Okay, so I don't think we're going to get around to talking about why type synonyms are kind of bad in this particular beginner class, but they're not great. All right, so we know that we're going to take in one string argument for this, right? Or do we? The functions we were looking at that convert characters, do they work on strings? No, they work on individual characters, right? Right. We were looking at using toLower, right? And it works on individual characters. But we have a list of characters. What are we going to do? That you're on the right track. Yes. And then we're going to make it recursive. People are staring at me like, oh my God, we don't know how to do that. All right. But yes, we do. Because we've looked at a recursive data type, and that's all we need to know about recursion. All right. So we are going to change our argument a little bit to look like this. Okay, so this is the first time we have really done it's really a pattern match, right? This deconstructs the list for us. Passing the argument in like this deconstructs the list into a head and the rest of the list. A head const onto the rest of the list. So that's the first thing that we need to do, right? Because we need to act on a character by character basis, recursively over the string. All right. Now, since someone, rather than do this just for this function, let's see if we can make a general one that will recurse over a list and apply a function to each element in the list. What should we call this function?
Pam.
Pam. I like it. Yes, it's a joke because there's a prelude function called map that is this, but we're about to implement it for ourselves, so we have to give it a different name. So Pam it will be. All right, we're going to write this general. We're going to use it on a string, but we're going to try to write this more generally, right? So we'll do this as for a list of A, or actually, first it has to take a function, doesn't it? All right, so we're going to start with an A to B function. Why A to B instead of A to A? It's more general to do A to B, right? We're going to go for maximum generality on this one. So it's more general to do it from A to B because that means that you could be transforming the values of the list into something that's even of another type. Now, in fact, with our ignore caps function, we are not going to be transforming them to a different type. They'll still be characters, but for maximum generality, we'll go A to B. So it would take a list of A then as its second argument, right? An A to B function would apply that A to B function to every element in the list of A and return for us a list of B. Okay, so now this is the function that we're going to write, and then we're going to use it in our ignore caps. So we'll still start by deconstructing the list, right? Well, actually, first we'll have a one-letter variable here that signifies our function. Oh, that's annoying. Let's just write it out. Function, right? Function is a variable name, though it's not any kind of keyword in Haskell. So this is just a generic word for a function, since our first argument here is some function, right? Okay, so then we will deconstruct our list so that we can apply the function to each element recursively in the list. Okay, so how are we going to do that? That's right. First, we're going to apply that transforming function to the first element of the list. What's our next step? Cons. Our next step is cons, because we are not mutating our list. God forbid. We don't do that in Haskell, right? We're not mutating our list. So we're not, if we've got a list, we're not going inside the list and mutating some value and returning them the same list, right? We have to rebuild the list, right? So we've deconstructed the list into its elements here. Now we have to reconstruct it here. Okay, so the function will apply to the first argument, and then we will append that to a list, and here's where we're going to recurse. Right. Huh? Yes, something function XS. Pam function XS. Whoops. Cannot type it all today. I'm really sorry. Okay. So what have we done here? Let me go ahead and make that big so you can see the whole thing. Or I could do that. Okay. So what have we done here? By calling the function itself, what are we doing? It is recursion, but why do we have to do it here? Why can't we just leave that part off and just apply the function to the rest of the x's? Right, because x's is a list. So we have to call the function again so that once again it will break the head off of the list and apply the function just to the head and then keep going. Does that make sense to everybody? Yes. 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 So sometimes you can, sometimes when we're being good teachers, we just go ahead and name our variables with descriptive names. So head and tail are built-in functions and how, in the prelude, and they're in the base library and stuff, but you can use them for variable names like this, and that's a little more mnemonic. So, of course, then I would have to change it, here, right, here, and here. Okay. Yes.
So how? So now we have the recursion, but I still don't see how the head gets bitten off.
So the head just gets bitten off here when we actually apply it to the argument. That's just what that does. Instead of like here, this is the whole string, right? And we haven't broken it apart at all. But you can break it apart here. You can break it apart as, when you apply the function to it. Yes.
How does it know where to stop?
How does it know where to stop? That's a good question. What's going to happen if we apply this to
How does the split work on empty?
Yeah. Well, I was getting there. Yeah, we have this, but what is going to happen let's start with what's going to happen if we apply this to an empty list. Let's reload this. What? I have a naked expression.
No caps isn't defined.
Oh, yeah. Well, we can fix that. Undefined. Perfect. Okay. Variable not in scope. What did I not change? Right here. Okay. Now we have satisfied it. Okay. So what's going to happen if we apply Pam here to an empty string?
It's caps. No, in your caps.
Yeah, no, we don't have it. We don't have any. We haven't taken care of the empty string yet.
We need to pass a function.
Oh yeah. Well, we have to do some function, right? Okay. So we've got a function now. Now we'll apply it to an empty list. And what'll happen? Oh yeah, bad things, right? Because we have not taken care of our empty list case. Now, we have to take care of the empty list case so that we don't throw this exception, and also so that our recursion has a place to stop. Of course, it won't ever stop if the list is infinite. But assuming we have a finite list, then it eventually will hit that empty list case, and that's how it'll stop. So we're just going to do a pattern match here. We're going to have function and an empty list. And that'll just return an empty list. All right, so now if we reload this, and now we can call Pam over some list We have to make sure it works, right? So what is this going to do?
Each element in the list will be +1.
Yes, right. It will add 1 to each element in the list, and then it should stop. All right, looks good. Should we check it with an empty list again and make sure? I mean, I think we're good. Yes, lovely. So now we can take this, and let's say we have an extremely excited taco cat. Oh dear. You know what's going to happen this time? Oh, there isn't a function. Sorry, I told you I can't think today. I do have, yes. Okay, so now we have our excited taco cat. Okay. There we go. So now it's mapping elements by elements to lower, right? So now we have a way to take care of the caps. And so now we can come back over here and write this function. I just did it in the REPL, so that should be easy enough to write, right? Oops. All right, any questions? No, everybody understands map. Yes? You understand Pam, yes. Not map. Okay, so let's make sure that is working. And we will give that, now we'll give that, there we go. Okay, so now what we want to do is change our main so that it works with, so that if we have, for example, if we call main and we give it taco cat. Oh, that, well, sure, that gave us true because that was all caps. Sure. Okay. We want to change that, change our main so that when we type in capital T, capital C, that we still get true. Okay, everybody got that working? Hmm? All right. All right, so personally, I like to keep my mains short when I can. There's no special reason that you have to do that. I just find I don't know. I just like it. I think it's just an aesthetic preference, really. So I did it like this. I made a new function that composed the two old functions, and then I used that in my main. All right, questions so far? Oh, yes.
Can you show how to write the same function in your space, if it's possible? The writing IQ instance or add IQ instance, which actually ignoring capital for free.
You want to
Yeah, I don't want to mutate data. I want to ignore
right.
them using reason.
You want to change the eq instance on our, that we're using.
Possible.
It would be possible.
For the same type, so with implementation.
No.
But
No.
No.
You would have to rename the type somehow. So what we would probably do, because you can't do that with a type synonym. Like string is a type synonym for a list of right? For a list of characters. So you actually have to give it what's called a new type, so that the type actually has a different name. So it would still be a string underneath, but it would have a different name, and then you can make different type class instances for that name. And so, sure, that would be a way that we could do that. Did everybody understand what he asked in the answer? Yeah? Okay. We'll talk about, I don't know if we'll get to new types a whole lot tomorrow, maybe a little bit. But new types are one of the ways that you can make types in Haskell. And like I said, they're just a different name for some underlying type. So if you have strings that you want to have a different type class instance, for example, you can give them a new name by making a new type wrapper and write different instances for them. There are other reasons why we use new types. So for example, there's really an unfortunate number of times, right, when you're passing around some string type and some integer type, for example, and you want to be able to keep track of what these different strings and integers represent in terms of like your logic. And so we often use new type wrappers for that as well. They're not really that hard to understand. I'm just not sure that they'll really come up tomorrow. So, but there are some cool features about new types, such as you can have different type class instances. Okay. All right, cool. We're about to get to folds then. All right. So the next thing I want to do, I know some people sometimes like to play with palindromes that are numbers. Yeah, well, there are numeric palindromes, right? And sometimes there's cool, like people who are really into number theory do cool things with number palindromes, right? But as I've said, as a linguist, I don't like numbers. So I want to make sure that in my palindrome checking program, that that everything contained in our string is actually an alphanumeric character, because they don't have to be for strings, right? Strings can contain numbers and control characters and all kinds of different characters, right? It can be enclosed within those quotation marks. But I want our palindromes to only do what we think of as words. Okay, so what I want to do next then is write a function that will check to make sure that every character in our string is an alphabetic character. So we've already seen that we have some functions in base that can check to see if things meet some condition, right? They are this set of functions here, right? Character classification functions, that's what they're called. And we have one here that looks at a character and returns a bool, returns true if it's an alphabetic character and false if it's not. So what we want to do is we want to do kind of a combination of things here, right? To get an answer for, is this an alphabetic word? We've got a function here that can tell us that for each character, So we could use Pam, right, and map that over each character, but then what would we end up with? A list of Booleans, which is not ideal at all. That's not what we want, right? We want to know, is every one of those list of Booleans, are all of them true? So what we want is a function called all. Unfortunately, there is a function called all that already exists in the prelude, so we're going to write our own, because writing our own is going to lead us to learning about folds, and folds are beautiful and wonderful things. All right, so first what we'll do is we can write all. Let's go here, and we have to give it, of course, a different name. So you can call it my all, or you can call it la. Right? So la is going to take oh dear. Okay. Yeah. Well, it's going to take a function from A to bool and a list of A, and it's going to return a bool. All right, so given what we've done with Pam already, we can probably fairly easily write this with recursion, right? Let's do that first, and then we'll talk about using a fold to do it instead. So we'll have a function and a list. I should tell you that with all, right, we're checking Booleans. So we do have this AND operator. Okay. An AND takes two bools and returns a bool and works like an AND, right? We have, if there's two trues, we get a true. If anything is false, we get false, right? So we'll tell you that we have that, but let's see how we can write our la function. La. All right. Yes. All right, so
empty list should be true or false.
oh yeah. Yeah.
Oh.
Yes. Because you just want to use the identity for that. Okay. So we're going to use oh, we actually want to use true for that, don't we? For the identity. Yeah. To stop the recursion as well. Okay, I think okay. Is everybody ready for me to go on, or do you want some more? Okay. I'm going to introduce you to a new syntax here. because this is going to be a very useful syntax. We're going to use this a lot tomorrow. So this is called a case expression. Now, a case expression lets us pattern match on values of a certain type. In this case, we're going to be doing it on Booleans. And because this returns a Boolean, so we're going to apply this function to this. And if we return, or actually just to the x, sorry, right? Because we're going element by element. So we're going to apply the function to x. And if that returns false, then what are we going to return? For a function like all, right, the way Booleans work, if we have even one false, what do we get? False, right? So we're going to, in our case expression here, we're going to apply that function to the head. Then for some reason, the syntax for case expressions goes case expression of. I don't really know what that of means, but that's how the syntax goes. So if applying function to x results in a false, then we return false for the whole thing. If it returns true, then what do we need to do?
Check on excess.
Yes, we need to check the rest of the list, right? So here's where our recursion is going to come in. Yes. LLA function excess. Right. Okay. So there are a lot of different ways that you could have written this, right? Because you could have done it, you know, just like we did here. I mean, yeah, you could have done it like this, right? Not with consing, of course, but with recursing in that style. But this case expression is why?
No.
Oh.
Looking at my code is not compiling it. It's like the same, but
what does it say?
no, it's don't worry.
Okay. Are you sure?
Why wouldn't you do it with the double ampersand?
Oh, I shouldn't have shown you the double ampersand yet because we're going to use that for the fold.
Okay. But you could use it here as well.
Huh?
You
could
use it here as well. It'd be similar.
You could. Is that how you did it?
Yeah, I did it like that.
Okay. Well, how did you do it? I thought you were going to tell us. I didn't know you wanted me to do it.
No, I had to look up because then I got concerned about the runtime framework.
Okay.
Well, that was a shortcut, short circuit logic in Haskell, but it seems that there is.
Yes, there is. That's why I wanted to do it like this, but we will use the double ampersand for the fold version.
Yeah.
Yep. So, I mean, here, basically, we wrote our short circuit logic right there, right? The first false that we hit, we'll just return false.
Yes, but I just wasn't aware that if you just did a trivial recursive function, like with the PAMP,
yeah,
that would also short circuit because
it will.
Of the logic.
Yep.
But then this is doing pattern matching and false.
Yes. Okay. Any more questions? Yes. 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 Yeah. Yep. I think so. I haven't actually benchmarked it or anything, but I think so. Yeah.
It won't.
It won't?
Because the way that that AND is implemented is that it will only evaluate the rest because of pattern matching on the left side of AND. So once it hits something which is false, then
so it wouldn't have any effect. Okay.
Because of the laziness.
Okay. Yeah, because of the laziness, it would have that same short circuiting behavior anyway. All right. Any more questions? Okay, cool. So now we're going to we have I guess I should try and make sure that mine actually compiles, but I think it does. It does. All right. So, but now I'm wanting you to write the all function, not really to introduce you to case expressions, although we will use them tomorrow, but to introduce you to folds. So we're going to, how many of you are familiar with folds? Okay. In Haskell, Scala, both? What? Huh? Okay. All right. So we're actually only going to talk about fold R. So there are right folds and there are left folds, and there are also folds. There's also a function called folds that that you don't think about whether it goes right or left. What we're going to talk about is fold R. Fold R. The R is for right. The right versus left at the end of the fold name refers to its associativity. So when we talk about the way that folds evaluate, we will talk about their associativity a bit. Okay, so fold R has a fantastic type signature. I don't actually think I can remember it off the top of my head. You could look for it in your REPL, of course. So A to B to B, so that's a function, right? The two arguments that returns a B. B, and a list of A, and then at the end it returns a B. All right, so here we have a function. This B here is sometimes called accumulator. We'll shorten that to ACK. Sometimes you'll see it in Haskell code as ACK, ACC, which is short for accumulator. Sometimes people call it the start value. It is very often an identity value for this function. So this value here will be used to start. It will be the first. It will be the first. So when it'll be the place that we start doing the function applications. So the first value that gets applied in here. Okay. So and then here's our list. We've been working with strings, but we're not going to care that those are characters for now, right? And it's going to return a B value at the end. So where map or PAM, as we called it, right? Map does something like this. You have map plus 1 over some list like 1, 2, and 3. Map works like plus 1, 2, plus 1. Oops. I left out the 1 entirely. Okay, we're just going to pretend that that's not there because I started with 2 down there. Right? Plus 3, right? So map sort of, it doesn't really, of course, mutate in place, and we don't want to think that it does. However, we can sort of conceptualize map as working like this, right? Map is always going to give us back a list of transformed values. Fold, on the other hand, does not always give us back a list. It can under some circumstances, but fold is more like, so let's say we have plus there, because we need a binary function, not a unary function, right? Map has the type A to B, right? Whereas this has A to B to B. So we have just a plus there instead of a partially applied plus. Then we'd have some starting value. We'll call it 0 since that's the identity for addition. And then we'd have, say, 1, 2, 3. Okay. So fold, the way this works is a little bit different from map. It is going to recurse over the list, but at the same time, it's going to be sort of deconstructing that list and possibly collapsing them into a single value. So with something like addition, what would happen is you would get a list of something like 1, 2, wait, instead of the commas here, I can't Okay, we're starting over because I'm making too many mistakes. All right, so foldr is going to with plus and 0 and 1, 2, 3. Foldr is going to do something like this. It's going to kind of deconstruct that list. So we're actually going to end up with 1 plus 2 plus 3 plus 0. And then this is going to give us back, right? Here's our start value, right? Because remember, this is A to B to B, and this is B, and here's our list of A's. So the A is the first input to the function, right? So here's an A from our list of A's, and here's our B start value. And so what's the result of this going to be? Yes. So this will equal 6. So foldr recurses over the list like map, but at the same time can sort of break down the list, right? It sort of can think of it as breaking it into its individual values and applying the function in between those values, or putting the binary operator in between those values, and then sort of collapsing it to a single value. All right, so since this is fold R, the right associative one, that's why we have the parentheses over here. Fold left will go the other way. We would have, I think it's technically 0 plus 1, then plus 2, then plus 3. So fold L associates like that.
The function is B to A.
Yeah.
Yeah, B, A, B.
Yes. Okay. So we're going to use fold R to rewrite our all function. All right. So we said, let's get this up here for us, that foldr has that type. Again, we have this foldable constraint that we're not going to really worry about. We're just going to pretend this T is a list of A. Okay, that T is the type constructor for a list, as far as we're concerned. And this time we are going to use the double ampersand. Okay, and so we're going to write an implementation now of this function using foldr. Everybody with me? Cool. So, oh dear. Okay. So we'll call this, or how about fold law? There we go. Yes, fold law. All right. So this time we'll have I told you that there's a function called all that already exists, right? So we can cheat a little bit and see the type of it there. Okay, so the function that we're writing needs to have the type A to bool, to list of A, bool.
What again EA means?
This?
Yeah.
So foldable is a type class.
Okay.
Yeah. So there are other data structures that are foldable, like lists. I mean, lists are sort of the canonical foldable data structure, but there are other foldable structures. And so we have a type class for some functions over foldable structures, and it's got the unfortunate name foldable. And so, yeah, we care about lists, but things like all will work on a lot of other data structures.
And when we create our own application, it's going to be foldable as well?
The what? I'm sorry.
We create our own dimensional list. It will be foldable.
Yes. Well, you can make it foldable. If you've renamed it, then you're going to have to come up with an instance of foldable yourself.
But by default, it will not be foldable.
Right. Because it only can check if something is an instance of a type class by the name of the type. Right. So if you've renamed it to something and it doesn't have the square brackets to look up the instance anymore, then you would have to make it an instance of foldable yourself, or you'd have to write the instance.
But doing so would be super down, so the compiler can do it.
Oh, yeah, we can derive them, but yeah.
Oh, just on the stash.
Yes. Yeah. Tomorrow when we're going to write some of our own types. And so when we write some types that, don't exist in base, then we'll have to have instances for them ourselves, and we will talk about if you do need to write one, how to do that, and we will also talk about how you can just derive them. Because, I said, like earlier, I said show is a type class that takes your data and makes printable strings to show on the screen. That's a type class, but you rarely write your own show instance. You usually need a show instance if you're going to be wanting to print anything to the terminal. You need a show instance, but you would rarely write that by yourself. So you just derive them. So we'll go over both of those tomorrow. All right. So how are we coming with our fold law here? All right, so we're going to have a function again and a list of x's. Do you need a couple more minutes? Okay, since the first function that's for fold R needs to take 2 arguments, right? So you need to deconstruct your list further than we have deconstructed our lists so far. You need to get the first 2 elements out of the list. Because remember, our first argument to fold R, right? Our first argument to fold R needs 2 inputs. So when we were doing, map or PAM, and we were going to use it with something that goes just from character to bool, and so we only needed 1 input. We only had to pattern match 1 head off the list, right? But now we need 2 of them. We need 2 elements.
Can you just start with true, but
All right. So I'm not here teaching you typing because I'm really bad at that apparently. All right. So does anybody know what we do next? We've got two elements here. Yes, then we'll need our function, but we also need to be able to pass two of these arguments to our function. And then we'll need a start value, which because it's all, we will want to use true. That's the identity. All right, so we're going to do, we are going to use the ampersand. Yep, we're going to use this function here. So what we're going to do is this. Have you ever seen this before? Huh? Yes, it's an anonymous function. That's right. So this gives us a way, because we pattern match these guys out of our list right here, but we need a way within the fold to actually pass them to this function. Right? And so now we can apply our function, because it's an A to bool function, to X. XS?
And then
nope. We just want to apply it because it only takes an A, not the list of A. We're not there yet. We're still, so fold R takes this A to B function first. Okay, I'll line it up maybe better. So here I have it already written. So we'll look at this one. Okay, because this anonymous syntax is really hard to understand. So this F here is our A to bool function, right? Okay.
Y isn't of type A.
Y is definitely of type A because it came from a list of A.
So how can you and Y directly?
How can you and Y directly?
Don't you apply F to Y also in order to get to Boolean?
You would think so, but this gets into how folds evaluate. The reason we don't apply F to Y here is because, all right. Oh, I have my green. Okay, so if you remember here how fold R evaluates, our start value is going to go here at the end of the evaluation, right? And our start value, in this case, our start value here is true, right? And so we have this, and when we start evaluating this fold, let's say we got, what are we actually folding over? Okay. We have an A to bool function. It's a character to bool, right? So what we're actually going to have is alpha here, right? So this isn't a bool, true, right? And then here's going to be our list of A's. Okay, so when it starts evaluating this, because we know we're using is alpha with our function, right? Oh, sorry. Well, all is going to equal fold R, and then A. What we want is an A to bool function, right? Because we want to use is alpha there. but it's an A to B to B, right? So this has to be a bool. Because the first argument of fold R is A to B to B, and we know that we want to end up with a bool here, right? And so these have to be bools, right? When it starts evaluating this, the reason that we don't apply F to Y there is because this start value will go at the end of the evaluation. And so it will be function applied to X, ampersand, ampersand, Y, and the very first Y will be true. Because it associates like this.
Y is not the Y we define just above. In the head and tail. In head second. The Y there is not the same Y as in the.
Oh, no.
Okay, that was.
Oh, yeah.
Okay.
Yes.
Okay. Now
yes.
Where I got wrong.
Okay. Yeah. Yeah. No, it's okay. So this is one of the problems with the. What are we going to call this one though? Neck. Okay. All right. And so, yeah, these are not necessarily the same X and Y, right? We're going to, and then that's going to be a true. So, and then this will, evaluate to true or false, right? The application of F and X, F to X will evaluate to true or false. And then the ampersand will compare the two sides and reduce to one value. And then it'll recurse because fold R is magic. Yeah. Right, because so the double ampersand, which is the function that we're actually folding over the list, right? Because our actual, okay, this function here that we're actually folding over our list, right, is the ampersand. This was misleading. Ignore that, sorry. Right? Okay, so fold R, then we've got our A to B function is going to be this, right? Well, we have to pass it some arguments, but that's the function that we're actually folding over the list, right? And then we give it the identity value true, and then we'll give it a list of somethings, right?
They must be booleans.
They must be booleans, right? Then we would give it a list of booleans. So if we folded this, over this list, then as it evaluates this list, right, it's going to, for example, let's say we have a list of true, and then false will make the end of the list. So this true is going to come at the end of the list, right? It would say true and wow. Okay. False and this true goes here. Right? Our start value goes here, and so when we pass that X and the Y anonymously into this function, this function needs them both to be booleans already, right? So by applying our function, that is A to bool to X, X becomes a bool, and Y already is a bool because it associates to the right. Does that make sense?
I was taking the easy path, making all the lists directly boolean with PUM.
Nice.
Well, I mean,
yeah,
that is false.
Huh?
That is false because there is one false.
Yes, it will. The whole thing will reduce to false. Yes. Well, let me rewrite. But as you can see, my typing is not better than my writing, so I'm just gonna. All right, we've got 2 ampersands. We've got true as our identity, and then let's give them to a list of true. We'll cut down a little bit and only have that, right? So when this starts evaluating, we have to pass each of these, right, as arguments to this, right? Because this needs Booleans as arguments. And so it'll evaluate like this, true and I think technically the other way, but that's all right. False and that start value, right? That's there. And so that's why when we're talking about passing in X's and Y's from a list of characters, right? Because we have to transform those characters into Booleans to be able to use this, right? So we have to apply our function to X to get it to reduce to a bool so that we can then compare it to the true that we started with. Now, this whole thing will actually, like if this was false, if the application of function to X was false, then it will immediately stop and return false and we'll be done.
Why do we even drop off the head and
Why do we need to remove 2 elements?
because folder you
Oh, yeah.
here.
Yes. Huh? Well, we weren't ignoring the neck element, but yes. Huh? Yes, because you're right. The elements of the list are not what we're passing to the function necessarily, right? Yeah. Okay, so there we go. Yes, you can use the you can do that without pattern matching it. Sorry about that. Yes.
Why fold as a description of foldable key? The opposite would be just transform list to boolean. Why do we need apply fold function? So why define the like this?
Because do you mean why do we have a foldable constraint here? Because you always, but we're always using it with a list. Is that what you're asking?
Yeah, we can define. We can say the signature function, so we transform a list to a type. So A to bool in this case.
Yeah.
Why do we need this type class constraint?
Well, because what if this T wasn't a list? What if it was a binary tree, or I don't know, a set, or
we say that it is a list to bool. So
well, we said that because we're working with lists.
Type is not defined like we did list to bool, and it has a definition foldable type.
Because, like I said, we want our functions to be as generic as possible.
So it's less generic, no?
Huh? No, this is more generic than if we had list of A to bool. Because there's a bunch of types that have a foldable instance. Not all types, but a bunch of them. So tuples have a foldable type. Binary trees. A lot of things that you think of as containers or collections for a bunch of values can be foldable. And so by making all more generic, then we can use all with other kinds of data structures. So our all that we wrote only for lists, right? We wrote ours only for lists. And so we can only use the all that we wrote for lists. We can't use it on a binary tree or on a, yeah. Yes, this is more general. Okay, sorry about the. Sorry, I hate when I make mistakes when I'm teaching.
We've seen how to take 2 elements out of the list.
Now you have seen how to take 2 elements of the list, and it does work. You can do things with them. We just didn't actually need to do it for that one. The funny thing is, it works either way. It works when if you deconstruct it like that in this fold, it still works exactly the same way, because I guess it doesn't care. It recognizes that you didn't need to do that, and it just doesn't care, and it just works the way it's supposed to. So, all right. So we are now 10 minutes after 6. So I'm really, really amazed that we got through everything that we got through today. How's it going? Do we feel like we're learning Haskell? Yes? Okay. So I did write a blog post here about folds and infinite lists and how they work. So instead of talking about, because one of the questions that has come up in the past when I have taught people about folds has been, well, how can you fold over an infinite list? It would never, ever stop. That's not always true. There are, of course, many cases where it would never, ever stop, but there are ways that there are short-circuiting strategies. This blog post also talks more about fold L, if you want to know more about left folds and how left folds and right folds can evaluate differently, because they do evaluate differently. They don't only associate differently, they also evaluate differently. And so this blog post talks more about that if you are interested. All right, so tomorrow we will talk more about types and type classes, and then we're going to start talking about some of the big type classes that everybody loves, like functor, applicative, and monad. If we got this much done today, then I'm certain that we'll get through monad tomorrow. I'm very excited.
Thank you.